Great, today we're going to work with percent composition. So percent composition, we have seen this a little bit before, but we're going to look at it from a different angle to figure out the percent composition. So it is the mass of each element in a compound compared to the entire mass of the compound, and then since it's a percent, we multiply it by 100%. So in example, we'll look at CH4, which is methane. The first thing you want to do is calculate what is the mass for 1 mole. We know how to do that using the atomic masses off the periodic table and the number of atoms for each element present in the substance. So we have 1 carbon, atomic mass off the periodic table, we get our mass for carbon. Same for hydrogen, we have 4 hydrogen atoms times the mass from the periodic table, we get our total mass for that. So here's the total mass for the substance, for the compound, for CH4, that's the molar mass. Now, to do the percent of each compound, we would take carbon, and we would take the mass of the carbon that's present, which you have up above is 12.01 grams, divided by the total mass, which is right here, 16.05, times 100%, and this would give us our percent composition for carbon, which would be about 74.8%. Doing it for the other substance, hydrogen, the mass for the hydrogen was 4.04 divided by the total mass again times 100% gave us a percent of 25.2% of hydrogen. Notice those 2% should add up to be 100%. My second example for percent composition could be an example like this. If I had 2.45 grams of aluminum oxide, it decomposes into 1.3 grams of aluminum and 1.15 grams of oxygen. We want to know the percent composition of each one of these. It would be the same thing. I would take the percent of oxygen. To figure that out, I'm going to take that and I'm going to divide the amount of oxygen divided by the amount of the compound, the aluminum oxide. So this is the total that I have for the substance, and then this is for the oxygen. So I'm going to just take the amount of oxygen divided by the amount of the aluminum oxide, and I would get my percent of 46.9%. Okay, the next one for the other substance, I'm going to take the amount of aluminum, and the amount of aluminum, I'm going to subtract 2.45 minus the 1.15. That should tell me how much aluminum I have in there by subtracting out the oxygen, and I get my percent for that. Notice my 2% still add up to be 100% for my compound for the percent composition. We are also going to look at determining the empirical formula. Remember, the empirical formula of a compound gives the simplest whole number ratio of the atoms of the elements in the compound derived from data evidence. Okay, so we did this with figuring out the empirical formula for zinc chloride. So my first example for this one will be, what is the empirical formula for a compound that contains 2.644 grams of gold and 0.46 grams of chlorine? Remember, when we want to compare one substance to another in chemistry, we always need to convert to moles, because moles is relating particles, and that's how substances react to each other. It is particle by particle. So I would do my conversion for my chlorine. I have the mass, and then I looked up the periodic table to see what the atomic mass of chlorine was, and I have my moles. I would do the same thing for the gold. I had 2.644 grams of gold. I'm going to take it times 1 mole of gold over 196.97 grams of gold, and I get my moles for the gold. Notice, what we usually do is we look at these two and we compare them. Whichever one is the smallest, we take it into the other one. Okay, it looks like these two values are the same. So wouldn't that tell us that the gold and the chlorine are a 1 to 1 ratio. So it could be written as Cl AuCl. Notice down here I did write those in as what those were, but we know whenever we write a formula, it's always a small whole number ratio. And so if I took 0.01434 divided by itself, it would be 1. So it's a 1-to-1 ratio. The substance would be called gold 1 chloride. So here's another example of determining empirical formulas. Sometimes they're going to be slightly different. So this is the 4th example in here. So they want to know, what is the empirical formula for a compound that is made of 5.75 grams of sodium, 3.5 grams of nitrogen, and 12 grams of oxygen. Remember, we cannot compare mass to mass. We have to convert these to moles. That is always our first step. Remember, moles is the unit that's going to help us go from that step to particles to masses. So we want to look at what the ratio is here. So first we're going to find the moles of each one of those. So for sodium, I would take the mass of sodium that I have times 1 mole over 22.99 grams of sodium. Off of the periodic table, I get my moles of sodium. Then I need to do it for another substance, for nitrogen. I had 3.5 grams. I'm going to take it times 1 mole over 14.01 grams of sodium, or for nitrogen, and I get my moles for that. And then my last one would be oxygen. I'm going to take that and convert that one also to moles. So if I look at this, on my empirical formula, I look at my moles. I have this, this, and this. So I'm going to take these and I'm going to divide them by the smallest moles. This is going to be 1. This one would be also 1. And this one would be 3. So that's telling me that I have 1 sodium, 1 nitrogen, and 3 oxygens present in that ratio. So that would be the empirical formula for this substance. Okay? I could also write it as this, the moles, but remember, we're always going to convert these to a small whole number ratio. We're not going to leave them in a decimal number. So we divide those by the smallest amount of moles that we have present. This substance would be called sodium nitrate. The final thing that we're going to determine in this chapter or unit is going to be molecular formula. So the molecular formula of a substance is the formula that gives the actual number of atoms of each element in a molecular compound. Now, empirical formula is the simplest whole number ratio, which is determined by data from a lab that was done, which we did with the zinc chloride. So here would be an example of this. So one thing about these examples, they're going to be they're going to give you more information. So here's hydrogen peroxide. They told you it has a molar mass of 34 grams per mole, and it has a chemical composition of 5.9% hydrogen and 94.1% oxygen. They want to know, what is the molecular formula? So we're going to work this problem out on the next slide. It looks like this. So to figure out the molecular formula, first we got to find the empirical formula, which we just did. And when we do this, when they give us percents, if you assume that you have a 100-gram sample, then the percents become masses. So now we have 5.90 grams of hydrogen times, we got to convert them to moles just like we did with the other ones. 1 mole of hydrogen, remember, is 1.01 grams of hydrogen. Get that to cancel out. When I do this, I got 5.84 moles of hydrogen. Okay. Now I need to do the same thing for oxygen. I had 94.1% of oxygen. We're just going to convert that to grams. We're going to say we have a 100-gram sample, so this would be my 100-gram sample. taking this times 1 mole of oxygen is 16 grams of oxygen off of the periodic table. This gives us 5.88 moles. Now, if we look at these two, those two numbers are pretty identical. So we take this one, and if we divide it by 5.84, we would get 1. And if we did this one, we would get 1.00 something. So this looks like that it is a 1-to-1 ratio. Okay, so it looks like our empirical formula equals HO. It's a 1-to-1 ratio. Now, for the next part, we want to figure out, so it says we want to find the mass of the empirical formula. So we found out that the empirical formula was H and O. So we have H. We know the mass of H. There's 1 atom times 1.01. Gives me 1.01. And then for O, there is also 1 atom, because it was HO times 16. So it looks like the mass of this is 17.01. Okay, so that would be the molar mass of the empirical formula. Now, to figure out, they told us in the problem on the previous slide that the molar mass of the compound was 34 grams. So what we're going to do is we're going to divide the molar mass given, so that was 34 grams on the previous slide, per mole, divided by the empirical formula molar mass. Does another ratio for us, and it is 2. Okay, so here's what we do, is we take the empirical formula, which we had was HO, and we take it times 2. So what we would do is we times the subscripts that are down below here. If I did that, I would get H2O2. That would be called hydrogen peroxide. So that would be our molecular formula for this compound. So what we're doing is we're just looking at comparing the molar mass given, and they have to give it to you in the problem, to what the molar mass is for the empirical formula. How many times it goes in there, you need to multiply the empirical formula subscripts by that value. So just to sum up, what we've had in this unit so far is we've been using Avogadro's hypothesis that he used to count molecules by weighing macroscopic samples. Okay, so remember they started with gases, and they made the assumption that in a gas, if it's kept at the same conditions, that the number of particles that are in there are constant for any type of gas. And so that's where they developed the concept of the mole. And so for masses of that, then they could also determine the relative mass of individual molecules. Remember, relative masses, they took it and they compared it to another substance. Back in the early days, they compared it to hydrogen, but today we compare it to carbon because it's much more abundant and it's much more stable. So the other thing that we could do with this, since they could figure out and convert from how much stuff to how many particles, that is the concept of the mole. So we're using the molar masses of elements, we're using the masses and formulas of compounds and determining those, and we can also figure out empirical and molecular formulas. Empirical formulas have to be figured out from data, where molecular formulas could be calculated.